For this little video, we're going to take a look at signal 159, a diminutive little ground signal. Now here's 159, our ground signal, and we have two routes off it. Route 1 takes us to the left up here, and route 2 takes us across up to the next ground signal down here, where you can then shunt back. So we're going to concentrate on route 1, taking it across to the left. So here we have our two switches, route 1 for the main and route 2 for the goods. This is the OCS panel, so it's laid out with individual switches for each route. Starting at the left of the diagram, we have our switch for our signal. So we have our signal number and the route, as previously mentioned, and the switch has been operated to the reverse. So we've cleared that route. Following it along, we go through our point controls and our WZRs. If we've cleared our route for our points to operate, they will be across. If not, through the WZRs, the point available to be called, and that will then allow us to go through. Now this is our cross protection circuit, so if we are clearing our signal route 1, then we have to have our normal relay down. Remember I mentioned that a bit like a lever, the lever is either normal or reverse. If it's at normal, the signal is on at danger. If it is reverse, the signal is cleared at proceed. So here, to be able to proceed the signal, we have to prove it is also not on. What we don't want is a conflict in the relays where we have a normal and a reverse up at the same time, a signal proved on and off at the same time. So to be able to clear our signal, we want to prove that we are not also requesting it to go back to danger. So that will be up to start with. This will then operate, by which time this will then drop out quickly. This can be a problem if you're in relay rooms that have a lot of feeds off a single bus bar, and the voltage drops off so quickly that before the RR can pick, the NR's dropped. So this momentarily holds itself up while this operates, then this quickly drops out. Once that has dropped out, because this is already picked, it's already held up through its own back contact. This is the front contact of this relay. So it's a pick and stick circuit. But to start with initially, this must be up. This quickly picks, this quickly drops out. Then it will hold through its own contact. Looking at the next part of the circuit now, having picked the RR, we want to pick the RLR, the reverse lock or latching relay. So we're now at the stage where we have our signals at normal, our signals at danger for both routes, route 1 and route 2. Following it through, our normal NR is up, because we haven't cleared that yet, that is still in the normal. Our NR is up, we haven't cleared the signal yet. We're free of approach locking, and our track circuits, that concerned circuits, are up and clear, not occupied. Moving along, we have not yet put the signal to reverse, our lever to reverse, so our RLR will be down. Our normal latched relay will therefore be energised, picked up. Now, when we clear the signal to the opposite line, we break one of these to clear our route. What will happen is we need to drive down our NLR and pick up our RLR. You can only have one of them up at a time. So as you can appreciate, whilst the NLR is picked, the RLR will be down. So to be able to release the RLR, the second part of the circuit, the dotted line there underneath, confirming that part of this is an action in another relay. So to be able to release that, we have to pick this. To be able to release this, we have to pick that. So this is currently picked up, and we remove the feed off that. In removing the feed off that, we also need to energise the release side of it. So we will release the RLR, and that will energise. So it's a very quick momentary action, but what you don't want is you don't want both of them dropping at the same time, because one has to pick the other first before it drops out. You saw on the previous page that we were going to delatch our NLR and clear our RLR to clear our route. So here you can see that now the RR route relay has operated for route 1. that the opposite route for another signal as part of this, in fact there's 2 of them, 3 of them, these have not been operated, so we don't have conflicting routes. So these are NLRs, our normal route, locked routes for them are still engaged, so we haven't operated another route, and our other circuits that are required as part of this are all in their correct positions. Now we see that our NLR has delatched, it has dropped down, allowing us to pick our signal RLR for that route, route 1, and that picks up. So here we have our 159 routes. So this is route 1 NLR and route 1 RLR for 159, which is what we're just looking at. And you will notice straight away that these have red fronts on them. This implies that it is a latched relay. If these were removed and the relay was up, it would remain up. It is magnetically latched in that position. You have to drive the secondary coil in there, which is the dotted coil that you saw in the diagrams, to be able to delatch them magnetically. You have to destroy that magnetic field inside to delatch them. When one of these relays fails, we have a test set that is used to put that relay into the correct position. So as part of the tests, the maintainer will look at this and go, this relay has failed, right, what position is it in? Is it up or down? And then the replacement relay will be in the same position. It used to be senior testers used to be able to strap the circuit to get that into the correct position. We as maintainers are not allowed to do that. We have a test set that puts that into that position. That's how we do that. You may be lucky that the relay you get out the stores is in the correct position to start with. It just depends. But that's what this red band signifies. Now comes the really technical part, and I won't go too deep into this. This is where we have now requested our release of our route, and we now need to start moving points. So the interlocking will start to see what points are free to be called, and we'll start to call them. Very briefly, we're going to look at the WZR circuit. Now, the way to look at this from a perspective, if you're not familiar with the equipment, everything to the right of the WZR, we'll use this one here, everything to the right of this is the button side up in the signal box. So the signalman has, and you'll see from the next bit of the video, he has 3 positions on his points. Normally they should sit in the C, the centre position, and when he calls a route he will simply operate his signals button to button, or he will have route switches as he does here, you'll see that in the video, but normally it sits in the centre position. And what that does, that allows a 50 volt feed, which is all the way down here, sorry here in this case, this 50 volt feed to flow through to the centre. In flowing through to the centre, it goes through to the WZR. So that's telling the interlocking that I am free to be called. If you need to move these points, and that's these points 353s in this case. What the signalman has an ability to do is to flip the point switch to normal and reverse to operate the points, say for signal testing or for setting a route should there be a fault, because he has a route list that he must follow if there's a fault. So he presets all the routes, and then that takes the interlocking out of the equation to a certain degree, so these points will not automatically call themselves over, so the route is locked. And when that happens, you can put the switches into normal or reverse. And by doing that, it puts the feeds round to these sides here. Everything to the left is the interlocking. This is all the interlocking running itself. If permission is allowed to be able to move these points, all these circuits will align to allow the feed down. If not, they will not allow him to do it. So even though he can request reverse and normal, nothing will happen if the interlocking does not agree. So as long as the points are in the centre position, the interlocking runs the show, calls the WZR, calls the points. If, however, the signalman decides I'm going to put these reverse, he will drive the RLR. If he decides to call them normal, get round to it, he will drive the NLR. And as I mentioned before, that is the pick or energise part of the circuit, and there is also a release part of the circuit, because if you energise the normal locked relay, you must release the reverse locked relay. You cannot have both of these in the same state at the same time. Only one can be requested. You're either going normal or you're going reverse. So, as, say for instance in this case, we will call a normal, we will energise the normal, we must also, cross protection wise, have our reverses down. So we're proving that to get the normal we cannot have a reverse. Likewise in our reverse we must also not have a normal. We also prove the NLRs as well, proving that the switches are in the same positions as we're requesting, which is also repeated there. And then by the same token we allowed our feeds to go around. So if we're going for normal, so here we're reverse, we have no normal, but we did have to start with from our interlocking to drive that to release. So when our WZR here is energised, when this relay is picked, our WZR is energised, it allows the releasing functions. If we were to request the normal to be energised, no reverse, RLR down, can't go this way. So our interlocking is driving this move to clear our NLR. So everything from this side is the interlocking being in agreement. This side is a manual from the signaller requesting normal or reverse, or having a switch in the centre to allow the WZR to be free to call the points across. And you'll notice that the feeds from the releases are joined together. The feeds from the release on one side drives to the NLR back on the other side, and vice versa. The RLR, the refeed across the release on the NLR on the opposite side. Bit of a complex circuit, but just remember, WZR points free to be called, interlocking, panel request. Normally lies in the centre position to allow the negative feed through to the WZR. And here, as previously mentioned, is our point key. So as you can see, it sits normally in the centre, and the centre light will be non-illuminated. When we command it normal, it goes to the normal position. These points last were in the normal, and when the route is set, they will automatically, indication will go out, go over, the opposite indication will move to suit whichever route is selected. And when we're done and we want to put everything back onto the panel, we'll set it back into the centre position again. This is the flashing out of correspondence light in the centre if we don't get our detection within the allotted time, 7.5 seconds. Finally, now we're at the end, with all our controlling relays being in the correct positions for our points, our tracks and our other lamp proving and signals, we can clear our route checking or proving stick relay, and that will stick up and hold. These links here are our route links, so should we need to disconnect for signalling works or permanent way works, we can pull those pins out, and that will prevent the UCSR from therefore clearing the signals out on the ground further down the line. And I'll show you them in a second. And these are our route links. They are simply a pull pin instead of a slippable link. You can take the pin out and you can maintain them while you have a disconnection in place. These little holes here are designed so once you take the pin out, you can actually sit it in that dead hole there. When you pull the pin out, as you'll see in a bit, it displays a little red mark around it, so you know that it is not fully in and it is taken out. And you can see then that they're disconnected. And these just take the place off 2BA links or OBA links instead. Here you can see we've disconnected some of the route links, and as I mentioned, we've put them into the standing peg holes on the side so we can see that they are there. And also you'll notice the little red line that is now apparent, so you can visually see, hello, something disconnected here. There you go. And all they are is little push pins. Over time it has been known for these to go high resistance. These are in a very good state actually, considering they've been in for about 20 odd years. They have little expanding touch points there that make the circuit inside. I'm going to briefly mention approach locking and the timer relays that we're going to use here. These are thermal element timer relays. What you have in here is a bimetallic strip, and there's two of them as you apply an electric current to the bimetallic strip, the differential between the top bimetallic strip and the bottom bimetallic strip, which are bonded together, causes one to heat up faster than the other, thereby bending the strip. It will act like a spring. Now, the thing about thermal element relays or timer relays of any kind, there is what is known as hot and cold proving. A timer relay, to function correctly, has to time itself. So when you energise this, yes, it will bend, that will break the contacts. That will make a set of other contacts which will then give you your time. It'll take a certain length of time for this to operate, to bend, to go across. If it was a motor timer, it would take a certain length of time for the motor to transfer around and make the other contacts. But that's the hot part of it. But then you also have to cold prove it, so you also have to make sure it goes back to where it was, because what you don't want is a timer relay, once it's timed, staying stuck in that position. Otherwise, it's never going to time. The next time you need to use it, it's already there. So that's not safe, so we have to prove it's gone back, so cold proved. So it will take a certain length of time for this to de-energise and go back to its original state, and it will take a certain length of time for the motor to spring load back to its original point. These are thermal element timer relays, and I'll have a look at the circuit for that now. Here we have one of our timer circuits for our timer relays, and if we look across here, we have our positive feeds to the left, with our track down and our signal red. It then initiates the timing sequence. Now we'll follow this through. Everything inside the dotted lines is inside that timer relay. It tells us the number of the signal or points, its root, time, stick circuit, and it tells us the time. So it's a track timer stick, and it's set at 90 seconds. So to follow this circuit through, we've mentioned we have our feed coming in here. The timed stick relay here will not be energised to start with, because our circuit wasn't fed. Now we're feeding our circuit, we flow into here. Now we've got two paths. We cannot go through this contact because this contact is down to start with. This contact, the JS, is the contact of this relay, and this relay is down to start with, because nothing has been feeding in from the left. So we can't go through that way, so we must go down. As we go down, we have our thermal heater elements, basically, for the contacts. Now, at the bottom we have our thermal element itself. This is the actual part that heats up the bimetallic strip, coil around that. So, our voltage flows down. It has a choice of going through two paths here. Now, we are going to go down and drop on the bottom one, because as we've already mentioned, our JS is not up, it is down, because our relay is not being powered. So our path is provided for our 50 volts to flow along through the contact of the relay, timer relay being down. Starts the thermal element timer by heating the coil, so the bimetallic strip now starts to bend. As a bimetallic strip starts to bend, it will eventually bend upwards and make its top contact, this one. Breaking this contact, its back contact. As it breaks its back contact, it breaks off any potential feed through to output circuits. But it's already down as well, because this contact is still not made either, as is that one. So we started to heat, the back contact is broken, the front contact is now made. We have completed our circuit to making the timed part of the circuit that I mentioned, but as I mentioned, we have to cool it down again and go back to our original position. So as this contact makes, having timed, it picks the JS picks and sticks, because this is its own contact, so now the voltage can flow down and hold this up. As it holds the JS up, this contact makes, and of course because the JS is now energised and made its front contact, it breaks its back contact. As it breaks its back contact, it takes away the feed to the heating coil. So now the contact starts to cool down and go back again. It now breaks its thermal heating front contact as it's cooling down, but it doesn't matter, it will not kill off the JS because this is held across its front contact there, it's a pick and stick circuit. And as it makes its back contact again, it makes its output. JS is already held, it's picked and sticked, and off it goes, it makes its output circuit. So it's proved that it was timed and reset. Now when we break any of the input controls again, the whole thing starts again. The JS de-energizes, contact breaks, and we start again, back contact makes, we're ready and set up for timing again, and so forth and so forth.